All right. Well, welcome back, everybody. Your first week of classes is wrapping up well. Um, I would like to begin today's lecture by asking anybody if you have any questions or confusions about the key ideas in Unit 1 or the quiz that you took. Um, whatever question you have, I'm going to take note of it and either answer right away or make sure that I plan my lecture so I can answer those questions.
Just real fast, for anyone that's like not talking, can you just mute your mic so that it doesn't echo for the rest of us? I'd appreciate it.
Yeah, thank you.
Hate to be that guy, but
thanks, Scott. But
at the end of I think it was like the first example when you were talking about induction, I guess I just kind of got confused by like the algebra. Like I think the final algebra steps kind of tripped me up a little bit.
Okay. Careful with algebra. Okay, I'm going to talk about it later when we get there, but thanks for bringing it up. Anything else? Yeah, was there a raised hand? Sorry, I can only see a subset of you at a time because, no? Okay, so let me start then talking. And of course, if any sort of questions or confusion arises as I'm talking, please interrupt me, unmute yourself and be like, hey, stop, repeat, clarify, and so on and so forth, okay? Cool. So the main idea of this first unit is to become a little bit familiar with what does it mean to prove a mathematical statement. And the main points that I want to convey is that there's not just one way to prove a mathematical statement, and there is not an algorithm to prove a mathematical statement. And I've chosen to illustrate this with a couple examples rather than talk a lot about the theory of what it means to prove mathematical statements. But maybe just to sort of at least put a minimum amount of theory, right? Let me spend like a couple minutes again explaining this first paragraph that is meaning to say, what are we doing when we're trying to prove something, right? So the ingredients for a mathematical statement or a theorem, if you want, are two, right? There's hypothesis, and then there's the thesis. Okay, and hypothesis is what we assume to be true, right? So we work under the assumption that whatever you say in the hypothesis is true. So you don't have to check it, you don't have to verify it, you don't have to believe it, it's just true, right? It's not an opinion, right? And the thesis is what you want to show, what is not obviously true, but you want to show that it follows from the hypothesis. Okay. And so a mathematical statement, you can think of it as, you have a set of hypotheses, you have a thesis, and what you want to show is that, and what we denote by this symbol, by this double arrow, right, is that the hypothesis imply the thesis, which means that if the hypothesis hold, then the thesis is true. Okay? And typically this is not obvious, right? It's something that, it's sometimes surprising, sometimes not surprising, but it's not clear why it should be true, right? And so writing a proof really means breaking down this implication into a sequence of other mathematical statements that are in a sense smaller, and each of which is sort of obvious to yourself and to the person that you're proving things to, right? So these are, obvious statements. Okay. So it's not clear why from H it follows T, but I can take a smaller step and show you that from H follows this other statement S1. And then I can take another smaller step and show that if S1 holds, then S2 holds, and that's also obvious. And finally, I can break it down into, for example, a third step, that if S2 holds, then T holds. And now the implication that H implies T, which is not obvious, I've broken it up into 3 obvious implications. And so these 3 implications consist of a proof. Okay. And this is a schematic diagram, but each of these little diagrams where I put the arrows is often going to be presented as a sentence in the English language, right? It's not, something of the form, if this holds, then this holds because blah, blah, blah. Okay. Any questions, comments? Is this clear so far? Okay, like I said, I think these things come to life if you see a bunch of examples rather than us spending a lot of time talking about abstraction, right? So let's go straight on to our first example of our first mathematical statement, which is right here. Right? So the sum of the first n odd natural numbers is equal to n squared. Okay. So first of all, I've rewritten these statements in a couple different ways, right? This way is equivalent to this one by establishing a pattern. Right? When I write 1 plus 3 plus 5, what you see is that 1 is the first odd number, 3 is the second odd number, 5 is the third odd number. And so when I put plus dot, 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 we all should understand that the next sum is 7, the one after is 9, and you keep going until you get to the number 2n minus 1, and then you stop. And this sum, 1 plus 3 plus 5 plus 7 plus 9 plus dot, dot, dot plus 2n minus 1, we claim is equal to n squared. And again, the third example is just the mathematical notation, right? The summation notation, right? And this sigma is just means sum the values of a function, in this case, the function 2i minus 1, sum all values of this function when the input values are 1, 2, 3, all the way to n, right? This is what this notation reads. I know somebody in the quiz got confused by the fact that we had, instead of 2i minus 1, we had just 1, right? So this is a quick aside, right? If you're summing from 1 to n the function 1, right, you still have to evaluate this function for every I. You still have n summands, right? But because the function 1 is constant for every I, the output is always 1, right? So that's 1 plus 1 plus 1 plus 1 n times, and that's n, right? So if anybody was confused in the quiz, this is the explanation of why the quiz question was such. Okay. Any questions so far? Okay. So assuming that no question means that everything is clear, let me point out a couple, before we think about proving this statement, let me point out a couple things, right? So one thing is like, where are the hypotheses for this statement? Because in this case, we don't see them. And when we don't see them, well, the hypothesis is not that they're not there, they're just hidden, right? They're just that, you know, arithmetics, that we agree on the rule, on the basics of arithmetics, right? So the basics. Okay, so the hypothesis for the statement is that we agree on what integers are, we agree on what it means to be odd, we agree on what it means to add integers, and we agree on what it means to multiply integers, and we agree on what it means to say n squared, that n squared means n times n. Right? So these are the hypotheses. And obviously we don't say them because if every time you were to make a mathematical statement, you have to say all the things that you assume to be true in mathematics that have been established, then you never end, right? So in this case, the hypotheses are hidden. The other thing I want to point out is that this is, in fact, it's one statement, or it's really infinitely many statements, right? Because for every value you give to n, right, you have a different statement, right? You could argue that you have a statement s of 1, which is telling you that 1 is equal to 1 squared. You have a statement s of 2, which you obtain by plugging in n equals 2, which is saying that 1 plus 3 is equal to 2 squared, and so on and so forth. Okay? And so when you say something like this, the sum of the first n odd natural numbers is equal to n squared, right? Where really what you're saying is that for every value of n, s of n is true. Okay? And this thing for every, right? This thing is called a quantifier. And it's very important, and we'll come back to it in a unit or two. Okay? Cool. Again, if there's no questions, let me move on. And if there's questions, just unmute yourself and speak out. All right, so before you start proving a mathematical statement, it's always useful to test it, right? So like I said, our mathematical statement consisted in infinitely many equations, one for every n, right? And what we can do is, well, check that for the first few values of n, these equations hold, which is what we're doing here. Because if just one of these equations is wrong, doesn't check, then S is false. Okay? So when you check a mathematical statement that depends on n, if you find one value of n for which that statement is not true, then the whole statement is false. Okay? Now, what I've done here, right? I've checked from n1 to 5 that the statement is true for n is being 1 to 5. This provides a check that I'm not obviously cheating you, but this does not provide a proof, right? Because, well, the fact that this thing works for up to 5 doesn't guarantee that it's going to work for 7, right? And so on and so forth. And there's infinitely many values of n that I can choose. So I cannot actually prove this statement by going through every n and checking, right? So that's the question in the quiz that I think confused the most people, right? If I put, after n equals 5, I put etc., I'm not convincing anybody that this pattern has to continue, right? Only if you've believed me, right? But you should never believe, right? Your instructor, you should never believe anybody when you're, when you're asking for a proof, okay? So the check of the first 5 cases plus etc., it's not a proof, right? It's wishful thinking, right? Right? So a proof consists in like not asking somebody to believe etc., but to show them that etc. holds, to convince them, to convince a skeptic that etc. holds. Okay? Cool.
A quick question.
Yeah.
So if we were to test 1 through 5 or whatever, and we found one that was false, would we still need to write a proof that just says this is false because, and then use that one number as proof?
Yes. Yes.
Okay.
So to prove that that a statement is false, right, it's sufficient to find a counterexample to the statement, right? So if you want to show that for every n, S of n is this particular equation, and you find one n for which that is false, then you say this statement is false because for n equals 7, the equation is not satisfied. And that is a proof of the statement being false. Okay? Absolutely. Yeah, thanks for the observation. Let me move on. All right, so one technique of proof of this statement, and actually let me go back to the example real quick, is called induction. And let me maybe draw a silly picture first, right? The way I think of induction is really like your statements are a bunch of domino pieces, right? You have S of 1, you have S of 2, you have S of 3, you have S of 4, and so on and so forth. Okay? And showing that a statement is true amounts to knocking down one of these tiles. Okay? So the idea that induction consists in 2 parts. And let me tell you the second part first. The second part is to show that if a tile falls, then it knocks down the next one. Okay. And the first step of induction consists in knocking down the first tile. Okay, so if you have a domino game such you can show the second one, that every tile falling will knock down the next. And then you knock down the first tile, you actually do knock this one down, right? Then all the tiles will actually fall, right? Because the first one will knock down the second one will knock down the third one will knock down the fourth, and so on and so forth. Okay? So now the analogy is that just replace knocking down with showing that it's true. Okay, so the first case, which is also called base case, if you replace knocking down with showing true, means to show that S of 1 is true. Okay. The second case is an implication, right? So you're assuming that a tile is falling, and you want to show that when that does, the next time falls, right? So this is called the inductive hypothesis. Sorry, it's called the inductive step. Ahead of myself, real quick. Inductive step. And the inductive step consists in showing that if S for a given value n, or actually let me use my favorite mathematical symbol, smiley, is true, then S of smiley plus 1 is true. Okay, but now smiley is a symbol that can represent any number. Okay, and so in the second part, in the inductive step, you're going to assume S of smiley to be true. So this is also called the inductive hypothesis. And you want to prove that S of smiley plus 1 is true. So this is also called the inductive thesis, if you want. Okay. So just how you should be convinced that if you have a domino game where each tile knocks down the next, and you know that you're knocking down the first tile, then all the tiles are going to be down. If you have a sequence of mathematical statement indexed by the natural numbers, S of n's, if you show that S of 1 is true, and that every S of n true will imply that S of n plus 1 is true, then all the S of n's are true, right? Because you've showed that S of 1 is true, and so then the inductive step tells you that S of 2 is true. But now you know that S of 2 is true, so you can apply the inductive step to S of 2, and that will show you that S of 3 is true, and so on and so forth. Okay, so this is sort of the theory behind proof by induction. So let's see how it works in this particular case, right? So the base case is to show that S of 1 is true, right? But S of 1 is right here. The first odd integer is equal to n squared, and this is true. This is just one statement to check, so we can check it explicitly, right? So this equation right here is the base case in the inductive hypothesis, okay? And now, we have to do the inductive step. Right? So now instead of smiley, I've used big N because it's a little easier to type, right? But so now I'm going to take S of big N as my inductive hypothesis, and I'm assuming that this is true. Okay, and what I want to show is down here, which is S of n plus 1. I want to show true. Okay, so the way that you do this is you usually start from what you want to show true, or maybe from one side of it, right? So for example, you can start by saying, okay, let me start from the left-hand side here. And let me build a chain of equalities that will eventually show me that this left-hand side is equal to n plus 1 squared. Okay, so the first step is to just put some parentheses around here, right? I can rewrite this 1 plus 3 plus 5 plus dot 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 plus 2n minus 1 plus 2n plus 1. This is exactly the same as what I have here, but I'm going to put some parentheses here. And if I want to be really pedantic, I would say this equality holds because addition is associative, which means that I can put parentheses however I want. Okay. Again, I would not take off points if you don't tell me that the reason that you can put parentheses is because addition is associative, because between you and me, which we all know these facts, right? But if one wanted to be really like explicit, that's the reason why these two steps are equal. Okay? At this point, what I notice is that the thing in the red parenthesis is actually the left-hand side of S of n. And so I can use the equality, I can use this equality right here because I'm assuming this true. Okay, so I can use the inductive hypothesis to replace, because the left-hand side is equal to the right-hand side, I can replace the thing in parentheses with n squared. Okay, so the quantity circled here in the second bubble is equal to the third bubble, because I've just take one of the summands, the one in parentheses, and replaced with something which is equal to it because of the inductive hypothesis. And now at this point, you just use algebra to say, oh, now I recognize that this is the binomial expansion on n plus 1, right? By foiling, if you do n plus 1 squared, you write it as n plus 1 times n plus 1, and then you foil, you'll come to n squared plus 2n plus 1. And so this is equal. Okay, so you see, this initial equality was not obvious, or at least did not have a tight motivation for why this would hold, right? But for each of these steps, I've given you a tight motivation of why the equality holds. Okay, so each of these steps, together with this explanation, constitutes a proof. Okay, now since I was now talking as I proved, I've graphically drawn this bubble and yada yada yada, right? Obviously, when you're writing a proof, you write sentences instead of talking and instead of doing bubbles, right? And what's written in the textbook is an example of how you can write a proof, right? So that's I don't want to just duplicate that, right? So okay, let me also notice that we have proved the statement now because we've proved the base case and we have proved the inductive step. Okay, so I hope I have in this process also addressed the question about the algebra in the inductive step. Is that clear? Whoever asked that question earlier?
Thank you. Yeah, totally.
Yeah,
Thank
Nicole?
you.
Okay, great. Cool. Okay, so again, I encourage you to, try your hand at some other proof by inductions and become comfortable with it. But I want to move on to a different proof of the same statement, okay, which is a proof by using geometry, to translation to a geometric problem. Okay? And so what I want to do is to show here, the goal is I want to show that S of n is equivalent to counting the pebbles in a particular distribution of pebbles, in a configuration of pebbles, in two different ways. Okay? So for example, every once in a while, suppose that I give you a four by four grid of pebbles. Okay? And I want to know how many pebbles are there, right? One way is, well, this is a square that has four pebbles as the base and four pebbles as the height. And so by my definition of multiplication, if I have four rows, each of which has four pebbles, right, I have a total of 4 by 4 pebbles. So this is one way that I can count these pebbles because they're arranged in this very nice regular shape, which is a square, right? And if a square, you can count the side, then you also know the area in a sense, okay? The second way that I can count these pebbles is by counting kind of hooks, in the sense that I can count sort of pebbles like this. And so in this case, I am summing over 4 hooks. Okay. And now I notice that the first hook has 1 pebble. The second hook has 3 pebbles. The third hook has 5 pebbles. And the fourth hook has 7 pebbles. Okay. So what I've done right now, right, I haven't proven yet my theorem, but I've shown that S of 4 is true because it coincides. It corresponds to these 2 different ways of counting these 16 pebbles. Okay. So the way that you now turn this intuition, this understanding, into a proof is to just describe this process, these 2 different ways of counting pebbles for a square that has side n pebbles, where it doesn't really matter what n is, right? Because now I've shown how to do it for 4, but for any n, you can certainly say, well, if I have a square of pebbles that has n pebbles as a side and n pebbles as a height, by multiplication, I have n rows, each of which has n pebbles. I have a total of n squared pebbles, right? So this first part generalizes. This is true for every n. Instead of 4, it's n times n. Similarly, no matter how big your square is, I can always subdivide it into hooks like this that grow, that start from the left lowest most pebble and then go around with this shape. There is always n of these hooks, right? Because there is 1 hook for each of the elements of the lowest row, right? So now my lowest row had 4 elements, and therefore I have 4 hooks. But if I had n elements, I would have n hooks. Right? And the hook in position I, right? We can count how many pebbles are in the hook in position I. Because, well, I have the whole column above it, right, which has I elements. And then I have, well, almost the whole row here, because I've already counted this last element, right? So now I'm only adding I minus 1. Okay, so the number of pebbles in the ith hook is equal to 2i minus 1. And so the way that this number 2 generalizes, right, is that I'm summing over n hooks And each hook, the ith hook, has 2i minus 1 elements. Okay. And so, because these are two ways to count the same number of pebbles, it follows that this summation is the second way of counting it is equal to the first way of counting it. And so the summation from I equals 1 to n of 2i minus 1 is n squared. So it follows that S of n is true for every n. Okay. So what went into this proof, right, was to establish a geometric construction that was true. This geometric construction was true for every value of n, and then show that this geometric construction allows us to count the number of pebbles in two different ways, and that these two different countings give us exactly S of n. And again, it's different when you have to write it as opposed to when you can speak it and write at the same time, but that's why the book is there, right? In the book, I've hopefully put enough detail to see how you should write a proof like this. Whereas when I'm speaking, obviously when you're speaking, you have the advantage that you can say words like hook and draw it and point to it and you understand, right? When you're writing, you have to be more precise, right? And so if you notice when you read the book, right, the hooks are described in this kind of unintuitive, slightly painful way where it says the ith hook is all the pebbles that have either the first coordinate equal to y or the second coordinate equal to y, so there, again, there's some advantage that comes when you can talk to people and point to a picture and establish a pattern, right? That when you're writing, you cannot do. But in the book, I've tried to show an example of how to do it the other way. Okay, cool. Questions, comments?
Yeah, I had a question.
Yeah.
Whenever you're like trying to prove something by like using a geometric tactic, do you always have to like in a formal write-up, do we always have to like describe like a plane like you did? Like you'll be like on the plane on all points x, y, such that x, y are integers, and then you define like the constraints on x and the constraints on y. Do we always have to do that?
Again, not necessarily, right? So first of all, depending on your problem, sometimes actually you're going to have a geometric construction which is not a plane construction, right? Sometimes it could be a three-dimensional things and so on and so forth, right? If you're able to draw a picture and talk to the person, and so of course you can describe, right now I described to you this proof without referring to the plane and the i's and the j's and the x and y's, right? But I was aided by the fact that I could talk to you and point to a picture, right? When you have to just write something, sometimes using coordinates, right? This coordinatization is a way to make it possible to give a precise description of what you're trying to say. So it's not, by all means, it's not necessary, right? But paradoxically, actually, even though it looks more complicated, it makes your life a little bit easier. It makes it easier to be precise. Because you could very well just write all that I said in words, but you have to write a lot more to precisely say what is a hook, right? So, but yeah, good question. There's always a little bit of ambiguity, right? So I would consider correct if you drew a picture for me without coordinates and say a hook is something of this shape in the picture, and the ith hook starts here at the ith column, I would consider that good, right? But somebody could be like, yeah, it is not precise enough. So it's all about, sort of understanding also who you're writing for. Cool. So finally, I want to get us started on the third approach, which then we'll use it to give another proof of this statement next time in the group work. And so we have these 3 theorems. Okay, so the first theorem, oh, sorry, we have some definitions, which I should, go away. We have these definitions first, right? I define 2 functions of n, right? H of n is a function of n in the sense that for every value of n, it produces another number, h of n. And h of n is the number of handshakes that happen if in a group of n persons, everybody shakes hands with everybody else exactly once. Okay, so if there's 2 persons, there's exactly 1 handshake. Right? If there's 3 persons, there is, well, 3 handshakes. No, is there? 1, 2, 3? Yes, 3 handshakes, right? And so on and so forth. G of m is the sum of the first m natural numbers. So it's something similar to what we were doing before. Okay? So in this case, is the sum of, let me write it, 1 plus 2 plus 3 plus ... plus m. So first we're adding all the odd numbers, now we're adding all natural numbers. Okay. And so then we're looking at 3 statements, 3 mathematical statements about these functions. The first statement is that h of n is equal to g of n minus 1. The second statement is a formula for h of n. The third statement is a formula for g of m. Okay? So what I want to point your attention to in the last 3 minutes of today is that these 3 statements are not independent of each other. You know, it's not possible that at random one of them is true and the other is false, right? Because if you substitute, so note, where's my writing device? Here. So let me say the 3 statements are not independent. Because if the first one and the second one are both true, then I have a formula for h, and I have a relationship between h and g, right? So then I can use the formula for h, but plug in the relationship between h and g to compute g. Right? So if I know that h of n is equal to g of n minus 1, this is the same by using a substitution that says that n minus 1 is equal to Smiley, of saying that h of Smiley plus 1 is equal to g of Smiley. Okay? But now I can just plug in by theorem. So this is theorem 1. Now here I can use theorem 2 by saying, okay, I have a formula for h of n for whatever n is. Let me plug in n equals smiley plus 1, right? And so this becomes 1/2 smiley plus 1 times smiley plus 1 minus 1. Which is 1/2 smiley plus 1 times smiley. But now, if you just let smiley equal to m, you see that that's exactly theorem T3. Okay. Now, I'm already out of time, so give me just 30 seconds to say you can do the same for T1 plus T3, and you show that that will imply T2, and T2 plus T3 will imply T1 by following the same argument, right? So anytime you show that any two of these statements are true, the third one is forced to be true. But now, and here's the gymnastic that I'm going to ask you to do, and come back if you're confused about it, and we can talk about it on next Wednesday. This also shows that if you establish one of them to be true, for example, if T1 is true, that implies that T2 and T3 are now equivalent. Well, because if you already know that T1 is true, you only need another one to show that the third one is true. So if you get that T2 is true, that the T2 is true, then T3 is true. And if you get the T3 is true, you already have T1, so then you get the T2 is true. Okay. So once you establish one of the three of them, the other two become equivalent. And so one way to prove, a theorem about the sum of the first n integers is to first show that theorem 1.1, that the sum of n integers is equal to a number of handshakes, and then prove a formula for the number of handshakes, for example. Okay, so sorry, I ended up rushing a little bit at the end because we're out of time, but spend a little bit of time. If you're confused, go on the discussion, go at it, ask questions. I will be moderating the discussion. I'll be, helping out and answering as much as possible. And then we can still talk about it on Wednesday, but then on Wednesday, the bulk of the hour will be devoted to tackling the problems in the second section of the book. Right. Cool. Well, thank you all very much. Have a good weekend, and looking forward to seeing you in person on Wednesday if nothing changes.
Thank you.
Right.
Have a good weekend, Renzo.
Thank you.
Thank you.
Thank you.
Yeah.
Thank you.